Okay, we are in chapter 11, and in chapter 11, we're going to look at systems of linear equations. Rather short chapter for us. We are only interested in two sections in chapter 11. The first section is kind of a review of systems of linear equations, and our focus is really on section 5, which I don't think you've seen anything like this yet. This is probably the first time you're looking at the title Partial Fraction Decomposition. So let's begin with section 11.1 for this video. Now, systems of linear equations, anytime we have, let's say, two or more equations, and we are interested in solving them simultaneously, find a common solution to each of them, then we have what we call a system. Okay, and there you have it. So here I have two equations. Both of them happen to be linear. That means if you graph each of these, the graph's going to be a line, and hence the name linear systems. So I have two equations. I'm interested in the common solution xy, the ordered pair xy that works in both of them, not one or the other. So for instance, let's say if I say x is 2, y is 3. I know 2 plus 3 is 5, correct? But will 2, 3 work in the second equation? In the second equation, if I go with ordered pair 2, 3, I'm going to get 4 plus 9, which does not equal to 7. Therefore, 2, 3 is not going to be a solution to this system. So how are we going to solve the system? Well, we can do it by a graphical method, which I really don't like. Graphical method, even in the case of two equations, two unknowns, not always works in that if you have to do it, let's say by hand, and construct a Cartesian coordinate system, unless the point of intersection of the lines, because remember the graph of these is going to be line, unless the point of intersection is an integer value, it's very difficult to solve or read the solution from the graphical grid. The other two analytical methods that I'm going to tell you about, that you know about already, is substitution and the elimination. Now, future sections, other sections of chapter 11 also talk about matrix method, determinant. So there's about a half a dozen different ways we can do this. Again, my focus is really getting to section 5, 11.5, partial fraction decomposition. And the reason I mention it here, section 11.1, is because in section 11.5, we're going to end up solving a system. Most likely. So for that reason, I need to do a review of section 1. All right, so let's take a look at, for instance, with the graphical method. Anytime we graph two equations, a number of possibilities could occur. So for instance, two lines may be parallel in that form. To have a common solution requires that the two lines would cross at a common point. And because these two parallel lines do not cross, so this is the case where the system is labeled as inconsistent system. Inconsistent systems have no solution. So whether it's two equations, two unknowns, in the case I have, or three equations, three unknowns, four equations, four unknowns, and whatever. As long as the system is inconsistent, it does not have a solution. All right. Now, the other possibility when we graph two lines that could happen is that we could have two crossing lines. Now, however they cross, wherever they cross, that common point of intersection, that's where the solution is. So that is why when we go to the graphical method, we graph and we look at the common point of intersection. In this case, the system is called a consistent system, and it has a unique solution. It has a single solution, one solution. Okay. And the other possibility when we graph two lines is that one line overlays on top of the other. In other words, these two lines are really the same lines. One overlays on top of the other. In that case, the system still remains consistent. The requirement for consistency, by the way, is to have at least one solution. So the system is consistent, and in this particular case, there are actually infinite number of solutions. Now, because there are infinite solutions, more specifically, these kind of systems are called as dependent systems. So these are dependent systems. Remember, dependent systems are consistent. Okay, and there you go. Now, the first case, in most practical applications, the first case doesn't do us any good. And sometimes having too many solutions doesn't help us either. So we are hoping that our solution is going to yield a single unique solution. All right, so let's take a look at an example here. I'm going to solve a system of 2 equations, 2 unknowns. And then later, we're going to look at 3 equations, 3 unknowns. So we go 5x minus y equal 21, and then you could have 2x plus 3y is equal to negative 12. Suppose I want to solve that system. Now I'm going to skip the graphing part. Okay, I'm going to graph it, in fact, using a software. And once I solve it, then we'll look at the graph. Rather than me doing it by hand, I'll use a software for this one. But let's take a look at the, first we're going to look at the substitution method. In substitution method, it requires that we choose a variable in one of the 2 equations. So you have a choice of x or y, you have choice of equation 1 or 2. So the one that we actually going to solve for, the variable, is usually, if we can, we choose the one that has a coefficient of 1. So if it's, for instance, if it's just x by itself or y by itself. Where the closest I can come to that is having y, negative y in the first equation. So I'm going to solve for y. Okay, first equation, I'm going to solve for y in equation 1. And this is number 1, this is equation 2. Now, how do I solve for y? Well, I can keep 5x, bring 21 to the left, becomes negative 21, and move y to the other side, becomes positive y. And there you go. So I solve for y. Now, once you solve for a variable of your choice and the equation of your choice, then you can simply substitute, hence the name substitution. We're going to substitute for y in the other equation, not the same one. If you put it in the same equation, you get 21 equal 21. So that's not going to help us. So I'm going to substitute in the second equation. In the second equation, the expression becomes 2x plus 3y, but then y is 5x negative 21. Correct? Equals negative 12. Next step, I need to isolate x because I have parentheses. We're going to use distributive property in order to combine like terms. 3 times 5, might as well write that as 15x. Negative 3 times 21 is 63 equals negative 12. Okay, and then I can solve this for x. Combine like terms, I get 17x. Add 63 to both sides. That makes it 51 on the right side. Divide both sides by 17. 17 times 3 is 51. So x must be 3. Okay, now when x is 3, I can actually substitute for x now in here and determine what the value of y should be. And I'm going to do that next. Therefore, that's going to give me 5 times 3, negative 21 is equal to y. That's 15, take away 21, or negative 6. Therefore, the value of y must be negative 6. All right, so there we go. And the solution, by the way, is going to be the ordered pair 3 comma negative 6. That means if we graph this system, the common point of intersection, there will be one, and it will be at 3, negative 6. Now, I've actually done that. I have graphed this system. So let me bring it up here for you so you can actually see this. And there we have it. Let me slide it a bit to the left and we're good. And there it is. Now the red line is 5x minus y equal 21. Here's the y-intercept at negative 21. And the blue line is 2x. This one is 2x plus 3y equals negative 12. Okay, that's what that one is. 2x plus 3y equal negative 12. Okay, and as you can see, the point of intersection is clearly at 3, negative 6. So it would be 1, 2, this would be 3, and this is negative 6. And you can clearly see that point of intersection. This is a solution, 3, negative 6. And that is what I was saying. This is a drawback of the graphical method. A couple of drawbacks. One, if the points are not integers, that's what these numbers are, integers. If they're not integers, like fractions, decimals, non-terminating decimal, imagine if the solution was 3.001372723, blah, blah, blah. Well, from the graph, we wouldn't be able to look that up, right? So that's one drawback. The point of intersection may not be integer. The biggest drawback also is that we cannot really graph beyond 3 dimensions. So graphical method has this limitation. It can be done up to 3 equations, 3 unknowns, and that's it. So our ideal method of solving systems going forward is going to be substitution, elimination, and those other analytical methods like matrix and determinants. All right. And there you have it. Again, good example of just a simple system. Hopefully this reminds you on how this was done. Let me take a look at one more example of, I'm going to look at, let's see, the elimination method now, actually. Same system. In fact, let's do this example that we just did. We just did elimination method. Now, substitution method. I like to do elimination method next for this example. So let's see how that's going to work out. Okay, to do elimination or use elimination method, we have a set of rules by which we can go by. These 3 rules that you see, these are called the elementary elementary operation on systems. Okay. So anytime we have a system of equation, we can create what we call equivalent systems of equations by doing any one of these 3 things that we're doing right now. So for example, I could interchange any 2 equations in the system. Well, for interchanging equation is just like writing the second equation first equation second. That's really not going to change the system, or the solution to the system, I should say. Rule number 2 of elementary operations on systems tells us that we can divide any equation in a system by a non-zero number, constant. So for example, we can multiply first equation by 7, second equation by negative 8. That's not going to change the solution. And this is partly true because remember, if you have an equation, you can multiply both sides of an equation by any constant. That's the multiplication rule of equations. So number 2 is really the multiplication rule of equations. Now number 3 is a little wordy. Sometimes we want to replace an equation with one that is easier to work with. So in this case, we say that if you want to replace any equation in a system, you can do that by replacing the equation you want to replace by sum of that equation and a constant multiple of another equation. Okay, that will eliminate the equation and replaces it actually. So remember, rule number 3 actually replaces, it gives you a whole new equation. Okay. Now, using elimination method, the idea is to follow these operations, elementary operation on systems, to where we can actually eliminate one of the variables. Okay, and quite often rule number 3 is what we use in order to do this. So for instance, let's see how we're going to do this. Let's say I'm going to eliminate y, and it doesn't matter, by the way, which one you eliminate, x or y. It's a little easier to eliminate y in this case than it is x, because x has 2 different coefficients. If you want to eliminate x, let's see, the LCD, or the least common multiple of 2 and 5, is 10, right? So I will multiply top equation by 2, the bottom by 5. One of them has to be negative, so to create opposites. So if I do that, the top equation, is going to become 10x negative 2y equals 42. The bottom equation is negative 10x negative 6y. I'm sorry, negative 5 times 3 is 15y equals 60. And then I can add the 2 equations. Okay, I'm doing number 3. See, it tells that you can replace it by the sum of. That means add it. So that's why I'm adding them. 2 and 15 makes negative 17y, and this would be 102. So y would be 102 divided by negative 17. And that would be negative 6. So in fact, there you go. We just solved this system for y, for variable y. Okay. Now, sorry about this. And once we solve for y, we can back substitute for y in either of the equations, because this is a system, it's got to work in both, and we can solve for x. So when y is negative 6, then I have 5x minus y equals 21. That's 5x plus 6 is 21. Subtract 6 from both sides, you get 15. So x must be 3. And again, we don't expect a different outcome. It's just a different method of solving the system. Now, what if I wanted to eliminate the y? That would have been a little easier to eliminate y's, because they're already opposite in sign. I need to multiply the top by 3. Okay. Now, multiplying the top equation by 3 times 5, 15x, negative 3y equals 63. Adding it to the second equation, which is 2x plus 3y equal negative 12. That will give me 17x equals to 51, so x must be 3. So notice I end up solving for x rather than y if I choose to eliminate y. But again, however you do this, you're going to get the same outcome. And I'm just going to put the answer for y from here. Okay, and there you go. That's what the elimination method is. Okay, now what if I have, let's say, 3 equations and 3 unknowns? If we have 3 equations and 3 unknowns, we can solve them again either using graphical method, substitution, or elimination, and the other methods that I'm not talking about. Now, graphing them, there you go. You solve 3 equations, 3 unknowns, a linear equation that is, then the graph's going to be a flat surface. Now, these flat surfaces, because I have 3 equations, 3 unknowns, right? We're looking at that one. 3 equations, 3 unknowns. Well, each of those equations, the graph of it is going to be a flat surface. Now, there are a number of ways these surfaces can come together, as you can see here. And this is not an exhaustive list, but those are the most common ways the three planes or surfaces, flat surfaces, could be drawn. The one that we hope for is that we have three planes crossing at a common point of intersection. In that case, the system is consistent and has a single unique solution. All right, that's again when the three planes come together at a common point. Or the three planes could come together in the form where there is a point of intersection, but not just a single one, but in this case, I have infinitely many points of intersections, right? So this is a system that is dependent now, isn't it? Notice the system is consistent. It has infinite number of solutions. And that same system is here, by the way. It's just the equations here are dependent. And you get the exact same outcome. The three planes could coincide, and again, that's another situation where you have infinite solutions. So look at infinite solution here. The cases where there's no solution would be three parallel planes. Remember, two parallel lines have no solution. Well, now three parallel planes have no solution. This one has no solution, right? Because again, the three of them should come together either at a single point or along a line or coincide. All of these have solutions. It's just there are infinite number of solutions, right? For these two and a single solution for that. All right. And we can also have no solution when two planes coincide and those two are parallel to the third plane. And that's how we can get, again, a system that is inconsistent. Okay. And let's see, but it does have two dependent equations here because those two surfaces coincide. And that's what this says. The equations are dependent. The system is inconsistent in this case because there's no point of intersection. So a number of things could happen. Now, graphical method is out of question for us because in order to do this, we have to learn how to graph in 3 dimensions, and that's not what the scope of this course is. However, I will do an example for you, and I'll use a software. I go to GeoGebra portal, and actually graph the planes, the surfaces for you. Okay, and then we'll be able to see some cool animation of the 3 surfaces that come together. So toward that goal, let's take a look at an example. And let's say the example I want to solve a system of 3 equations, 3 unknowns. So this is the example, by the way, that we're not going to have a solution in this one, but I want to show you what's going to happen. How can we not have a solution? So the second equation is 2z equals 0, and the last one, negative 2x plus 3y, negative 7z equals 1. I have a system of 3 equations, 3 unknowns. And I'm going to stay with the elimination method here. Using the elimination method, when you have 3 equations, 3 unknowns, what we need to do is first we need to pair these equations together. Now, when there are 3 equations and we want to create pairs, there are 3 possible pairings when you have 3 equations. So, for example, I could pair first equation and the third, first and second, or I can pair second and third. Those are the 3 possibilities, right? Now, before we pair them, we kind of do a cursory check and see which of the variables of between x, y, and z, which one is the easiest to get rid of, to eliminate. And again, this, for the system I have, I wouldn't eliminate z because it's going to take a little longer than x or y, because see these coefficients, 3 to negative 7, they really are not multiples of each other. So if the coefficients are multiples of each other, are a lot easier to get rid of. So for instance, in here, notice I have multiples. So there we go, 3, 3. But the 2 isn't. Looking at x, well, I can see 4 is a multiple of 2. 2 and negative 2, well, that's good. They're multiples of each other. And perfect. So that's what I want to do. Therefore, I would like to choose to eliminate x. Again, doesn't matter. You can eliminate anything, but some choices are better than others. The best choice for this system is x. So I want to get rid of x. In order to eliminate x, I'm going to pair the first equation, 2x negative 2y plus 3z equals 6. And the third one, negative 2x plus 3y negative 7z equal 1. And then I'm going to pair the second one, which is 4x negative 3y plus 2z equals 0, and pair it with the third one, negative 2x plus 3y negative 7z equal 1. All right. Now, let's eliminate x in the first pair. To eliminate x, all I gotta do is just add them, right? Add the two equations together. And that's something we can do with equations, right? We can simply add them together in a system. Now, 3y minus 2y, that's y. Negative 7 plus 3 is negative 4z. 6 and 1 makes 7. And there we have it. So we have y minus 4z equals 7. Notice x is gone. Now, in my second system that I have, remember my second pairing of the third and the second equation, I'm going to have to eliminate x again. Notice if I just add them, y disappears. So just because that's easier, it's not going to help me, because let's suppose I do add them together. Then I'm going to get 2x negative 5z equal 1, correct? And y is gone now. Well, what am I left with here? I have two equations, right? And I have three unknowns, x, y, and z. So I cannot solve this. All right. Therefore, whichever variable you choose to eliminate, you have to eliminate from both of these. Now, having said that, in order to eliminate x, I'm just going to multiply the bottom equation by 2. Okay, and so here's the top equation rewritten, and the new and improved bottom equation, second equation, is this one. Make sure 2 reaches to the other side of equal sign also, multiplies by 1. Not just on one side, you multiply both sides. And that was rule number 2 of systems of equations. You can multiply an equation in a system and it won't change the solution. They will give you an equivalent system. Now I have 3y negative 12z equals 2. Okay. So what do we do next? Well, next we're going to pair these together. Once we eliminate x, now we manage to reduce the system to 2 equations and 2 unknowns. The 2 unknowns are y and z. 3y negative 12z equals 2. And doesn't matter, again, you can eliminate y or z, whichever you choose to. Suppose I want to multiply the top by negative 3. I'm trying to eliminate my y. So the top equation is now negative 3y plus 12z is equal to negative 21. And then the bottom equation is 3y negative 12z equals 2. Remember, I wanted to get rid of y, and I did. And it just so happens that the z is also eliminated. Therefore, nothing on the left side. And to the right, I have negative 21 and 2, which makes negative 19. 0 equal to negative 19. that is not, and therefore we have a false statement. When you get a false statement, when the variables disappear, this is the sign that the system is inconsistent. Okay, and I'm just gonna write that. The system is inconsistent, and that just identifies the system. In the way of solution, we know inconsistent systems have no solution. Therefore, there's no solution in this one. So this system has no solution. All right. And there you have it. Now let's take a look at a system that actually has a solution, and then I will graph this. So here's my example. Let's say I have x negative 2y plus 3z equals 7, and then 2x plus y plus z equals 4. And my third equation, negative 3x plus 2y negative 2z equals negative 10. All right, and I want to solve this. I'm going to solve this system using elimination method. Okay, now a quick look at the variables here. I can see that a variable y would be the easiest one to eliminate, because I have a couple of 2's here, multiples of 2, and that those will pair nicely with the y, correct? So let's do that. I'm going to pair the first equation, x minus 2y plus 3z equals 7, and the second one, which is 2x plus y plus z equals 4. And then I'm going to pair the first and the third one, x minus 2y plus 3z equals 7, and negative 3x plus 2y negative 2z equals negative 10. So that's how we're going to pair them. Now for the first pair, I want to get rid of the y's, so I'm going to multiply the second equation by 2 to create opposites. Having done that, I'm going to multiply them. 2 by 2, 4x. The second equation is 4x plus 2y plus 2z equals 8. Then we're going to add first and third, these two equations together. X and 4x, that makes 5x. The y's are opposite, they add to 0, and I have 5z equals 15. Which works out nicely actually, because all three numbers are multiples of 5. So let's divide everything by 5. To divide by 5 is to multiply by 1/5, and that is a legit operation. Operation number 2, we can multiply by any constant. So there we have it. Now in the second pairing that I have, I'm going to eliminate the same variable y by simply adding the two equations together now. And when we add them together, we get negative 2x plus z equals negative 3. There's my second one. Now I'm going to pair these together. X plus z equals 3 and negative 2x plus z equals negative 3. And let's say I want to get rid of z here, so I'm just going to multiply the top equation by negative 1. Multiply by negative 1 makes the first equation negative x negative z equal negative 3, and the second equation is negative 2x plus z equal negative 3, and then add, becomes negative 3x equal negative 6, so x must be 2. And once I have a value for x, I can back substitute in here or in here, either one. I'm going to go in the one directly above. That says x plus z equals 3, so z must be 1. Once we have both x and z, we can go to any of the original equations in the system. Okay, and when we do that, I'm going to the second equation. I got 2x plus y plus z equals 4. So y must be, that's 5, subtract 5 from both sides, we get y is -1. Now the solution is in the form of an ordered triple again, x, y, z, alphabetical order. So it's going to be 2, -1, 1. And there we have the solution. Now, and that's it. The system is consistent as a common point of intersection of the three planes. So what I want to do next to finish off this section, that's all we want to do in this section. I'm going to actually go to a website and show you how these surfaces look. So I'm just gonna switch to my website, to my browser momentarily. Alrighty, so here we are. Now I'm using GeoGebra 3D calculator, and there's the URL for it. You can see up here, geogebra.org. Incredible software you can use. It'll do so many things, and it actually works in so many different languages. So I really encourage you to explore more of GeoGebra for your other courses. But here I have the three equations, by the way, that I just solved for in our system. Let's see, remember the equations I had were x minus 2y plus 3z equal, oh, this should be 7 here. Sorry, let me do that. Let me backspace and put a 7. All right. And there you go. Okay, so that was my first equation. X minus 2y plus 3z 7. The second one was 2x plus y plus z equal 4. The third one, negative 3x plus 2y minus 2z equals negative 10. All right. Now to the right, what you see is, you will probably see this, right? You recognize it as the rectangular coordinate system. The red is x, and it looks like it's two axes overlaid on top of each other, but for now just think of it as xy coordinate system. Now I can turn this into a three-dimensional coordinate system by simply doing what I'm doing right now, and there you have it. And this is my rectangular coordinate system, Cartesian coordinate system in 3 dimensions. This is going to be so cool, everyone. You're gonna love this. So just to for now, keep in mind the red is, oops, hold on. So this thing needs to cooperate with me, and it's cooperating. Okay, so this is I see. The red is x. Maybe I point to it. So this is the x-axis, the red. The black is the y-axis. So this is the y-axis, and red is the x, and the blue is the z-axis, with 3 equations and 3 unknowns, because we have 3 variables. So we have a 3-dimensional graph. Now, if let's say I want to graph the first one, I'm going to activate the first equation. There you go. So what you're looking at is the graph of the first equation. And here is the graph of it. You see what it looks like? This is what the surface looks like. You see that? Here's the surface. The green looking, light green or cyan, whatever the color is. And there you go. That's what the surface looks like. Alright, now I can actually move this thing around just to show you the surface a little bit better, and you can see it right there. You see that surface? You can look from underneath, and it goes forever in all directions, by the way, right? That surface. And something that's interesting, just to kind of give you a little bit on how these coordinate systems work. If I look at the surface to where it's almost like a line, right about there-ish. Hold on. Right here. You can see that this is the first equation. So when y and z are 0, x is 7, right? So that's this point right here. Right in here, x is 7. Okay, that's the point of intersection with the x-axis. See right there? This is 7. And when x and y are 0, z is 7/3. 7/3 is 2 1/3, and this is the point right up here on the blue axis. See, it's 2 1/3. And what about the y? Well, looks like the y is negative, isn't it? When z is 0, x is 0, y is negative 7/2, negative 3.5, and that's what this point is. This is negative 3.5 right there. Okay, so here's my first surface. All right, and again, you can look at the surface in all directions. My first equation. Now let's throw the second equation on top of this one. And there you go. This is now the second equation. So you're looking at how these two surfaces interact. The two equations are interacting together. Now to see a little bit better of what's going on with these two surfaces. So it looks like there is a common point of intersection, right? I mean, not point, but actually line. All of these, there you go, right along here is where the two surfaces cross, right there. Okay. And again, you can turn it around and look at it better. The point of intersections of the two is right there. Okay, the two lines, the two surfaces come together like that. And let me, there you go, I'm going to keep my XY coordinate system the way this. The way this works is x is, remember the red x is going in this direction, y is the black color, is this one, and blue is the z-axis. Now I'm going to throw in the third equation on top of it, and of course, the more surfaces we create, the more convoluted the shape gets, but there it is. Here's the third one. So that's how these three surfaces now come together. You can see, let me take the second one out. So this is how the first and the third equation come together. Okay, and this is how the first and the second one come together. When we throw again the third one on top of it, this is how all three of them come together. Okay. As you can see, graphically, this is going to be very cumbersome. Imagine if you had to graph this by hand. So it's going to be very difficult, extremely difficult to show this by hand. But again, we can see a better image of this thing. And this is so cool. You can actually look at this thing. There you go. And you can see this thing, oops, it's going a little fast. There. So you can see again how the three surfaces come together. And this animation hopefully helps you see what we mean by the point of intersection of three surfaces. For three equations, three unknowns. Now the equation that we found, the solution was 2, -1, 1. Which is still difficult to see. I wish the software would use different colors for the surfaces. Maybe that would have helped. But x is 2, so there you go. X is 2 right here. Z is 1. This is blue axis is z, so z is 1. That's right there, and y is -1 right there. So that's where the three come together. So you can go up from 2, go up 1. And over to y-axis, right about here in space. That's where the three come together. Okay. So this is GeoGebra. Give it a try. I think you'll like it. It'll do so many things beyond just what I'm doing here. But we are pretty much done with this lecture. That's all we wanted to cover in this section. In the next section, we're going to do actually something that's completely different. But I thought we'll cover one section, just a reminder on how to solve systems of linear equations. And let's see how the next section will go. So we're done. We're going to leave it on this nice animation, happy note. And hope to see you in my next lecture. Not to see you, you know what I mean. Hope to have you in another lecture. Thank you for watching, everyone, and take care. Thanks again.